Alright, so now you've read the problem for problem number 2A. The first thing we have to do, right, is we write our knowns and our unknowns. My camera's slipping, hold on. I apologize that you can see the edge of my makeshift tripod in this video, my bad. So the first thing we do, right, is we write our knowns and our unknowns, okay? And then we go through the problem. We know a starting pressure, a volume, a temperature. We always know R. We can write that down. Okay, and it wants to know the number of moles of our gas. So we do not see a change in our gas. This means we get to use the ideal gas law. Okay, and remember, Ms. Rosinsky gives us points if we write our equation down. So we're going to write PV equals nRT. Perfect. Okay, and then we also get points if we rearrange it so that what we want, what we're looking for, is written by itself on one side of the equation, right? So we're going to write N equals, and if we divide both sides by RT, then we get N by itself, okay? And now we can plug stuff in. Pressure. Oh, wait. Can we plug stuff in? What units do we need to have of everything? We need Kelvin, which we got. We need moles, which is what we're looking for. Okay. We need liters, which we've got, but we need atmospheres. We don't have atmospheres, we have torr. So before we can plug anything in, we're going to have to come down here and convert our torr to atmospheres. So we start with what we have, 840 torr. Okay. Our conversion factor is that 760 torr equals 1 atmosphere. Okay, so we'll write that right here. We want torr to cancel, so we'll write the torr on the bottom, 760 torr. Here's our ratio. 760 torr is 1 atmosphere. And when we plug into our calculator, 840 over 760, we're going to end up with 1.11 atmospheres. Okay, so now we can come back up here and plug stuff in. We have P is 1.11 atmospheres. We just calculated that. Volume, 3.5 liters. R, we always know, 0.0821 liters atmospheres per mole Kelvin. And remember, our units that we want to use for everything else, we're always going to go off the units of R. Everything else needs to match the units of R, our gas law constant. And we know temperature is 523 Kelvin. Okay. So, now when we plug all of this into a calculator, this is an equal sign. Sorry, it's not supposed to be a Z. It's an equal sign. We have 1.11 times 3.5 divided by 0.0821 divided by 523. If you see here in my calculator, I used our 1.11 number times 3.5, and instead of putting parentheses because I'm lazy, I just divided by 0.0821 and then I divided by 523 because I'm just going off of order of operations. It really doesn't matter which way you do, as long as if you're going to put 0.0821 times 523, you have to use parentheses. Either way, we get our answer of 0.0901. But we can take it to two significant figures and just put 0.09. Okay. We got to double check our units, make sure we got what we wanted. So we have an atmospheres on top, an atmospheres on bottom. We have Kelvin on bottom and Kelvin on top. We have liters on top and liters on bottom. And then we have moles, which is on the bottom of something that's on the bottom. That means that it is on top. So yay, we have the right unit. This is what we were looking for. Good job, good team, woo! Okay. Let's take a look at this again. If we have some junk, I'm just going to say we have 1 over our units of R, liters, atmospheres, per mole, Kelvin. Okay? That is the same thing as 1 divided by liters, atmospheres, per mole, Kelvin. Okay? And that is the same thing as 1 times, whenever we're dividing a fraction, we can just multiply and flip it. Mole Kelvin over liters, atmospheres. Which is why, when I was back over here in my other problem, was it this one? Yeah. I had atmospheres on top, liters on top. Okay, this is what I had before, right? So that is the same thing as atmospheres, liters over Kelvin times, or divided by liters, atmospheres over mole Kelvin. Okay? And that would be the same thing as flip it and multiply. And now everything cancels all nicely, and I'm left with moles, which is what I just did. Okay? If you don't want to go through all the trouble of rewriting it like this, where you have whatever units you've got divided by your gas law units, or your gas constant units, that's fine. You don't have to rewrite the whole thing if you're sure that you're not going to get confused. If you think you are going to get confused, you can rewrite, here are my units of everything else divided by my gas law, my gas constant units, okay? And that's totally okay for you to do. Or if your gas constant is on top, then you can write my gas constant divided by the other stuff. It all works out. Okay, so moving on to, I'll just use this paper for right now. Here is number 2, part B. We have the same gas as in part 1, which means we can write our knowns and our unknowns. Okay? We have the same gas as in part 1, and it's going to change this time, which means that our P1, V1, T1, and N1 are all the things that were true in part 1. Okay, so our N1 is that 0.09 we just found. Okay, our T1 is that, where did it go? 523 Kelvin. Our P1 is our 1.11 atmospheres, and our V1 is 3.5 liters. Okay. Alright, so we have the same gases in part 1, and now it's changing. It wants to know how many grams of our gas, and to find those grams, what we're going to have to do is find our moles, right? This is step 1, and this is step 2. Okay? So now, let's see, it also gave us a P2 equals 4 atmospheres, T2 equals 22 atmospheres, and, oh, not atmospheres, sorry guys, and that's not 22, that's 6 Kelvin, my bad. 622 Kelvin. And our V2 is 2 liters. Okay. So now we have a change going on. So that means we're going to use our combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. Okay? Beautiful. And we're going to rearrange for N2 because that's what we're looking for. So we have P1V1 T2 over N1T1. Oh, oops, hold on. Yeah. Nope. See, this is why you should write all your algebra down, because you mess up like me if you didn't. So let's try this again. If we multiply both sides by N2, then we end up with N2 equals P2V2 times N1T1 divided by T2T1V1. Okay? Now, we're going to skip to a new sheet of paper. I'm actually going to change to a spiral because I seem to be out of clean computer paper because I'm a college student. And we can now plug stuff in. Okay. N2 equals P2V2 N1T1 over T2T1V1. And if we're plugging stuff in, that means N2 equals 4 atmospheres times 2.0 liters times 0.09 moles times 523 Kelvin over 622 Kelvin times 1.11 atmospheres times 3.5 liters. Okay, we plug that all into our calculator. 4 times 2 times 0.09 times 523 divided by 622 divided by 1.11 divided by 3.5. And we get N2 equals 0.156 moles. Okay. 0.156 moles. And we actually want to find grams. So how do we get, I was not writing on the video for all of that. Sorry guys. Okay. Grams from moles. We have to start with whatever we have, 0.156 moles. And if we're going to cancel out moles and get grams, we're going to have to go with the molecular mass, the molecular weights, which, let's see, the problem said we were dealing with nitrogen gas. Nitrogen gas, please remember, is N2. Okay, nitrogen gas is N2 because nitrogen's a diatomic. It's in that little 7 on the periodic table, right? And nitrogen is 14.01 for 1 nitrogen, which means the molecular mass of nitrogen is 28.02 grams per 1 mole. 0.156 times 28.02 gives us 4.37 grams of nitrogen. And that's our answer. Yay! Go Team.